So Naif is going to be presenting a really cool paper about how we can, essentially a new GNN, which deals with one of the problems that most GNNs or message passing neural networks have, which is oversmoothing, which is as they get deeper, you have, so GNNs are focused on graphs and specifically calculating node representations of graphs. As you get deeper message passing neural networks, one issue you have is that all the node representations tend to converge to the same values, even though the nodes might be in very different parts of the graph and have started out with very different features. Also, there's some argument that the dynamics of the methods that they're using are good ways to approximate this graph, like graph functions on graphs. Anyway, that was a quick introduction, but I'm passing it over to Naif now.
Yeah, so hi everyone. So I'm a PhD student currently at work, and I'm sort of interning at MPlan. And so the work that I do in my PhD is sort of on sort of stochastic dynamical systems, and the work that I'm sort of currently doing now at MPlan is sort of with graph neural networks. So I thought this is sort of a nice sort of amalgamation of the two, where maybe I'm just a little bit biased, but it's always nice to think of sort of neural networks as these discrete versions of continuous processes, right? So this paper tries to apply the same sort of idea. So sort of motivated by PDEs, it sort of proposes some view of GCNs, so graph convolutional networks, as discretizations of PDEs on manifolds. And so a family of GCNs are sort of proposed in this paper, which utilize sort of the discrete graph operators as their basis, and then argue that it helps sort of solve problems, like Peter said, like oversmoothing. And also they mention sort of a big part of this paper is generalizability, and how certain graph neural network architectures can sort of have a bias towards different data types and different problems. So this paper tries to solve those two main problems. That's sort of oversmoothing and generalizability. And so it does this by sort of proposing two different PDE models. And at the end, so they do a lot of tests, actually, sort of lots of different data sets. And they show that it is sort of better or the same, sort of on par with current state-of-the-art results from different neural networks. Okay. So in the introduction, they do mention this sort of oversmoothing problem. And this oversmoothing is the fact that, so as you increase the depth of a GCN, the node features become more similar to each other. Sort of something like a low pass filter. And actually there's a paper that would be interesting to go through. It's called like GCNs or like graph neural networks are just low pass filters. And so this oversmoothing phenomenon is like a pretty big issue, and will make sort of the results that you get a lot worse as you increase the depth. And usually sort of that's what you sort of want to do, like increase the depth of your neural network, right? Usually. And with generalizability, what they mean is, so a GNN that so they don't want to have sort of a GNN that might perform better on one kind of data set than the other. So they want one unified model that can perform well on lots of different data sets. So those aren't just the two problems with GCNs or GNNs. You also, I guess, have the problem of poor performance on sort of long-range interactions in a graph. And there's also the problem of heterophilic data. So poor performance on heterophilic data. So as in where adjacent nodes have different labels. But those are sort of problems for sort of another paper, but this tries to solve oversmoothing and generalizability. So at first, I thought it would be good to sort of motivate neural networks as why you would sort of want to think of them as in sort of a continuous setting. And I mean, I could only think of sort of 3 points quickly, and I wrote them down here. So it's just easier to think about and analyze continuous systems than discrete ones, I think. So it's better, not that it's better, but it's sort of easier to think about, right? And then deep neural networks can be thought of as like discretizations of continuous dynamical systems. So the famous one is the ResNet. And it's been shown sort of CNNs are discretizations of PDEs. And third one, sort of most real-world models are represented using dynamical systems. So pretty much every single real-world process, there's going to be an ODE or PDE trying to model it. And so it would be nice to have some sort of combination of the theory and the analysis that you have from PDEs with some of the data that you have from machine learning models. So as an example, so consider this sort of dynamical system. Let me connect my tablet. Okay, yeah, that works. Okay, so if you consider this dynamical system, dz by dt is equals some function f. A here is a control at z0 is equal to x. And so the goal is to choose the control A such that this flow map at time capital T can be fitted accurately with a learned model U. So this learned model can be from any model, can be just linear regression. And so you want to minimize the loss between, let's say, a function y on your domain and this learned model U. And so you want to minimize this loss over this domain. And so you want your dynamical system and your model to be as close as possible, to sort of model the same dynamics. And so the connection with ResNet is, well, if you write down sort of the ResNet update with identity maps, it's just going to be sort of the representation Z at L plus 1 is just going to be the representation Z at L plus some function of Z and the weights at L, right? So if you've done any ODEs, you can see that this is a discretized version of the system dz by dt is equal to sort of f and w, where you said the time step delta t is equal to 1, right? So there's some inherent sort of similarities between looking at something like looking at a continuous system and a discretized version being some sort of like layers in your neural network. So that's sort of the main idea why you'd want to look at these networks in some continuous setting, is that they're super related to each other, and well, you have a lot of theory for dynamical systems that you can use. Okay, so the main type of neural network that this paper sort of tries to compare against are sort of graph networks.
Yeah, before we go any farther, so my understanding of the use of dynamical systems is basically that you view a neural network and its propagation from its first layer to its last layer as propagating a like a state through a dynamic system.
Yeah.
And to me, I don't actually feel like that has, because a neural network is really a mapping from like X to Y essentially. So I don't really feel like that has a like you could automatically say that this is how we should view these mappings. Like all mappings should be viewed as dynamic systems is essentially what I think they're saying here. And while I don't disagree with that, I also don't necessarily feel like there's a huge justification for it. So I'm just wondering why do you think it makes so much sense to like view like a neural network or any parameterized mapping like this as a dynamic system?
I guess my thinking is when you look at a neural network and you see sort of a lot of layers and lots of like updates with the layers, you have some sort of function that you keep updating layer by layer. And when it has some sort of this like super familiar structure like ResNets here, the first thing you can go sort of, I guess the first thing that I would think of is, okay, take the number of layers to infinity. You're going to have a dynamical system. You're going to have some sort of, and I guess then you can think of, okay, so I guess the neural network, what is it, an approximation of your sort of continuous dynamical system and so on. So I think it's just sort of thinking about the problem, but then in a different sort of setting where you're like, okay, let's look at equilibrium states or something like that. What is the solution approach to, and things like that. So, and I think it's useful in the sense of you can use the theory from dynamical systems to look at existence and uniqueness of solutions. Like, does a solution does it actually exist? So I think that's pretty important, that dynamical systems that can be applied to neural networks. But yeah, so I mean, for me, it's again this sort of like ResNet comparison. That sort of motivates the idea of you can think of neural nets as dynamical systems.
Okay, cool. Thanks.
Okay, so with graph convolutions, so just super simply, so graph convolutions, they aggregate features from local neighborhoods. So you have a node I, and then you aggregate. So you have the features at node I, and then you aggregate the features from its local neighborhood. And so a general message passing graph convolution network is, so you have your aggregation function here, H, you have your features, Fi, layer L, and then you sort of aggregate Fj around its neighborhood. And then you have some kernel G and your weights, right? And so you stack these layer on layer, and so you get the super simple graph convolutional network. And so here's a couple relevant ones that are sort of referenced a lot in the paper. So the first one is sort of the most famous graph convolutional network, where you have your features here, you have your weight matrix, and you have some Jacobian smoothing, so just some form of your Laplacian here with a nonlinearity. So it's the famous GCN model by Kipton Welling. And so in this model, as you stack your layers, as you increase L, you're going to sort of tend to over smooth. And so there's lots of papers that go into sort of, they do lots of numerical example of this and theoretical studies of this. And this is the case, and so you do get over smoothing. And so there's been lots of research to sort of try and mitigate this over smoothing problem. And so one of the main ones that they reference in this paper is sort of GCN II. So in this one, they have your features, F. And so you have two parts. So the first thing here is your initial residual connection. So whereas in normal ResNets, you have an input from your sort of features from your previous layer, here you consider the inputs from your initial layer. So like skip connections in ResNets, but it's the initial layer. And so this sort of allows to carry information from an initial representation. And the second part here is your identity mapping. So again, like ResNet, so it makes sure that you achieve at least the same performance as its shallow version. And so they show in this paper by Chen that residual connections in these graph convolution networks do prevent oversmoothing, or sort of do reduce oversmoothing. So there is lots of work towards this, but sort of this paper tries to sort of give a different approach on solving the oversmoothing problem. Okay. So again, so the four main parts of the paper, so they have some discretization of continuous operators on graphs. And so they have sort of a more general approach to the architecture design. And so they propose a variety of different graph problems that they solve with their PDE model. And it allows to construct deep networks without oversmoothing with some theoretical guarantees. Then they validate their method with lots of examples. So their lit review is pretty good, actually, what I thought. So they have sort of, they reference loads of different papers that try to solve different problems. So like there's DGCNN, which is sort of point cloud estimates, and the sort of the typical graph SAGE and GAT one networks. And so they do say that there are lots of methods that do try to solve this oversmoothing problem. So like this JKNet, where they combine sort of intermediate representations, and this GCN2, where you have this connection to ResNets. And then this next part here, I think is sort of the most important here. So there are networks that try to sort of inherently design some sort of update function that does not oversmooth. And so at the time that this paper was released, there was another paper at the same, pretty much at the same time, called Grand, by a team at I think Twitter, that applied the same idea of where you have sort of PDEs with graph convolutional networks, but sort of they apply some attention and they only consider sort of diffusive dynamics, whereas this paper looks at sort of diffusive and hyperbolic dynamics. So I thought sort of this paper was a bit of a better overview of the field. So it is sort of I feel like it's a popular area at the moment. Sort of in the last year or two, there's been a lot of papers out on looking at sort of graph networks as dynamic continuous systems on manifolds. So it is sort of an exciting area of research right now in graph data. And so there's been a lot of research on PDEs and CNNs and sort of the relationship between the two, where sort of there's lots of papers that show that CNNs are discretizations of PDEs, and where they use CNNs to help sort of your solutions to PDEs. So you can maybe choose sort of better initial conditions and so on. And there have been examples of where you use PDEs to improve your CNNs using the same sort of ResNet idea. And there has been work with sort of graph convolution networks to enhance the solutions for PDEs. And usually for these problems, they look at sort of fluid dynamics, because that's usually sort of the most interesting system where you have sort of lots of things going on in turbulence and so on. But anyway, so let's get into sort of the method. So they define their PDEs on manifolds instead of sort of Euclidean spaces. So they consider some general manifold M, where you have some vector function F on this manifold. And so with these sort of PDEs, you have your continuous operators. So you have your gradient, divergent, and your Laplacian. And with these, you can build up two different PDE systems. And so the systems that they have here is this nonlinear diffusion and nonlinear hyperbolic. So this is your diffusion, this is your hyperbolic. So if you you have some nonlinearity here as well. So if you set this nonlinearity to just be X, so for the first diffusion, you'll just get Ft is equal to divergence of K grad F, right? So assume some nice structure in K such that we can do this. So let's do K squared, then Laplacian F. Right, so this is your heat equation. And then if you do the same thing for the hyperbolic, you're just going to get your wave equation, right? So these are sort of the two main systems that they're looking at here. And so I thought before we sort of get into these two theorems, it might be good to go over the main ideas and why these two actual equations are important here in this case. And so some of the basics for a heat equation. So this is, I guess, the main idea is the heat operator. So it's smoothing in the sense, so it's doing some sort of smoothing in the sense that if you think of it as like a temperature, so the temperature at any point is the average, would be the average of the temperature in some ball around that point at a previous time. So you could run, so I guess this would be you at some point 0, x0 and xt. This is looking just 1D. So this would be some sort of average view around a ball of radius r around your point x0 at, let's say, time t0, tau 0, where tau 0 is less than t0, right? So it's some sort of smoothing operation. So you can think of, let's say, if you heat a rod at one end, you're going to just sort of get your heat diffusing throughout the rod, right? So this is what this equation is modeling. And a really nice thing about this is the maximum principle that you have. So if you define some sort of space-time rectangle here, where you sort of define your bounds as not to include 0 and L, and not to include t equals 0. So you have sort of all the points xt with t is equal to t belonging to this rectangle, but the points t equals 0, x equals 0, and x equals to L do not, right? But these points form what you call sort of a parabolic boundary here, right? So this is sort of the boundary of your domain and your initial condition, right? And so with this, you have sort of a theorem. So if you assume that U is has derivatives and they're differentiable and smooth and so on, so it solves the heat equation, and then the maximum minimum of U are attained on this parabolic boundary, gamma, right? And so that's really important and really useful for the heat equation, and I guess it shows some stability for your solutions, right? Because that's super important. You have boundary conditions in this case, and sort of Neumann boundary conditions. So you can think of it as sort of as your rectangular plate being insulated from the world, right? You're not getting any flux in and out of your plate. So this is a super important idea in this sort of heat equations, and I guess you can say that if you heat a plate at any time t, you're not going to get sort of a higher temperature at one point of the plate than one at the point that you heated it, basically. So that's sort of for the heat equation. And but this is a bit different than what they define here. So they have sort of a non-linear part there. And so what you would get is you just have to have some sort of assumption on your non-linearity. You can bound it by some sort of norm, and then you would have inequalities here. But it's still the same idea. Sort of your maximums and your minimums are bounded. And for the second one is the hyperbolic equation. And so just the wave equation. And the super important property on this one is the preservation of energy, right? So if you write the total energy in your system as the sum of the kinetic energy and the potential energy, then sort of the time variation of your energy is going to be equal to 0 with some assumptions that you have, such as like existence of integrals and so on. And so this is really important because then you can use this to show existence of uniqueness of solutions with the wave equation, right? And so they have a super nice, I feel like it's a really nice plot here where they initialize this mesh of sort of a human in this position with, I think it's just like random noise. And they solve, or sort of they integrate this forward in time in both systems. So in the sort of diffusive case, you can see everything at sort of every point in the node is just going towards some sort of some point is just going sort of diffusing out. And in the hyperbolic case, I guess it's not super clear here, but as in like you can see that things aren't sort of dying out, right? You're getting some conservation, like there's still sort of energy there. You have your conservation of energy. So these are the two sort of different systems that they introduce there. And they have these two theorems. So theorem 1 is pretty much your maximum principle, right? So it's showing that, so it has a non-increasing feature norm. So the feature norm does not increase with time, right? And the second theorem is your energy is bounded, basically. So the proofs of these are pretty, I think, I guess I can just go through them super quickly. They're not very sort of complicated. So for the first one, what you can do is sort of you take an inner product of the diffusion equation with F. So that's going to be F and then divergence of K adjoint sigma K grad F. And then what you can do is you can sort of integrate this by parts in time. So if you do just integration by parts, you'll get here half norm of F squared is going to be equal to minus the inner product K grad. That wouldn't be K then, not yet. This would be grad f and then k adjoint sigma k grad f. And the boundary terms, they vanish because of sort of your condition, your initial conditions and your boundary conditions. And so you can use the property of sort of this adjoint of k. So this will be minus k grad f, and then the nonlinearity, and then k grad f here. So what you do here is sort of now is use the sign property of your nonlinearity, right? As in, so your sign of k grad f is going to be equal to your sign of nonlinearity k grad f. And I misspelled sign there, but never mind. So you know that this inner product here is going to be positive. And so you have this and because you have this minus here, then you can say that half norm squared is going to be equal to, it's going to be less than or equal to 0. Right, and so then there's a time derivative there, d by dt, and d by dt. Right, so there you go. So that's pretty simple and pretty quickly. So that's your feature norms being non-increasing in time. And for the second one, the proof for the second theorem is perseverance using this energy conservation argument. So the way linear, so the energy for the linear hyperbolic.
And if I think you're cutting in and out a bit.
Can you hear me?
Seems like it got better again.
Oh, sorry. Yeah, maybe my internet's being dodgy. But anyway, so the energy for the linear hyperbolic is going to be, so energy linear one is going to be the kinetic energy plus your potential energy, which is going to be your inner product grad f. Right, and so then if you take the time derivative of this, so you'd get half dt. So linear energy is going to be equal to the inner product of ft minus divergence of k adjoint k grad f. Right, and then that's equal to 0 if you do that computation. And so I guess what you can say then is that there exists sort of a constant ck such that the energy in the linear system is equal to this constant ck. And so now what you would do is sort of use the nonlinearity. You would bring in the nonlinearity. So now using the nonlinear hyperbolic function, hyperbolic system. So now E net is the energy in the nonlinear hyperbolic equation. That's going to be, again, so the kinetic energy plus the norm, sorry, the inner product, k grad f, and then the nonlinear, k grad f. Right, and so now you use an assumption in the theorem. So in the theorem, they state that your nonlinearity is sort of bound by the norm, i.e. nonlinearity of x is less than or equal to the norm of x. And so we can say now that that's going to be less than or equal to the kinetic energy plus k grad f, k grad f, which is your the linear energy. So this would be your linear energy And so then your energy in the nonlinear hyperbolic system is bound by the CK, right? So you have some sort of energy bound. So that's the proof for theorem 2. I don't think they're sort of they use sort of very similar ideas to the same sort of problems that you do on sort of the Euclidean space. But these are sort of the main two proofs or the main two statements in the theorem where they can say that, okay, we have some theoretical sort of bounds on what you on your solutions. Yeah. Okay. And so theorem 1 is says for smoothing, and the second one is for sort of conserving energy. And interestingly, so they say that both of them have sort of different applications. So for the denoisers, for the diffusion one, so they reference to anisotropic diffusion. So I haven't sort of done much on sort of image segmentation and denoising, but this is sort of the typical model that they have for that sort of application. And the other one is for if you want to preserve the geometry in your data. So you use your energy conservation model, the hyperbolic model. So they have an example here, sort of protein folding and so on. So these are the two PDE models that you have. And so now you have to discretize them, right? So to actually do some sort of layer by layer update, right? You have to have a discretized version of these. And so they have a discretized version of the gradient, which is here. So this is a mapping from your vertices to your edges. And with some weight matrix, W. And then you can sort of define your divergence, where your sort of divergence is just going to be the adjoint of your graph gradient. Right, so it's pretty much here. So let's see, angle brackets. So it's the gradient of F and Q, which is Q is just an edge feature vector now. F is a node feature vector. And so this is, I guess this is sort of a discrete Stokes theorem if you write it out and you sort of define your Riemann manifold and so on. And so then you have your typical discrete Laplacian there. And they define some weighted line integral over an edge as well, but that they use that sort of just once in the paper. And so with these discretized representations of the continuous operators, they can then define sort of an update, layer by layer update, using the PDE models. And so for the diffusion model, they just use sort of forward Euler, and for the hyperbolic, they just use sort of the leapfrog method. And so this GF is going to be your gradient of F, and then you have some convolution kernel, and so on. H is going to be your time step when you think of discretizations of the models.
I've got a question about they say like in the discrete version, the Laplacian is G transpose G instead of minus G transpose G. Doesn't it change the whole dynamics? Taking the opposite of the Laplacian. Because then you don't have, like, for example, you don't have a wave equation. You have like something like D'Alembertian or something like that. I don't know.
I guess, yeah, because if you have a different sign for your Laplacian, then you're not going to get sort of diffusion, right?
Yeah.
But I guess their definition of, the definition that they use in sort of graph or network literature doesn't have this this negative. And if they don't have this negative, then your solution is going to blow up, right? So you do need this minus there. So I guess that's why they just say, okay, so this is going to be a minus there because you need this for sort of solution. Yeah. Oh. Down there. Yeah. else? So what else about this? Yeah, so that's pretty much the model, your discretized model. Interestingly, they don't look into other discretization methods for this, which I feel like they should. And they should sort of have some sort of analysis on your step size and so on. But yeah, they just say that you choose your step size such that your solution doesn't blow up, or such that you actually do get a solution, which, okay, sure. And yeah, and so they use sort of the hyperbolic tangent for the nonlinearity. And so they have a couple layers here. So you do a little bit of pre-processing, I guess, along the data. So you have this convolutional layer before you feed it into this PDE GCN network, which is just sort of pointwise convolution. And then if you sort of want to do your to solve sort of your model using edge features instead of the vertex features, then you can sort of just take the divergence and then average, right? Which I thought was pretty interesting, and sort of concatenates into the input embedding layer. I'm not exactly 100% sure how they came up with this form here, but yeah, I guess it makes sense, because I guess the divergence is a mapping from edge to vertex and so on, but yeah. And so in your output layer, you have your vertex features, and then you have your final sort of convolutional layer mapping sort of your hidden feature space into your output feature space. And they initialize the convolutions as identity. So they call it a sort of a prior to your model, which is, I don't know, I felt like it's interesting, but it makes sense, right? Because you sort of initialize as just the PDE itself, and then you sort of let this kernel vary as you train the model. So then you're sort of maybe looking at dynamics slightly different from the original sort of diffusion or hyperbolic equation dynamics, but yeah, but it still works. And so they have a mixture model here as well. So they have some alpha parameter here, where you can sort of train this parameter alpha, where the model can choose either more of a diffusion centric process or sort of a hyperbolic process. And yeah, and so yeah, let's get to the experiments. So they say that the node classification is typically solved with diffusion, and ones where you have sort of like meshes that you have to preserve geometry, then you have to use sort of your energy preserving hyperbolic system. Okay, so now sort of the metrics. So this DGCNN is for these point cloud, this point cloud data. So you get sort of pretty good, so really good accuracy on this model 10 data set. And they show that, okay, so if you apply this data set on this sort of node classification, you get pretty bad results, right? And then so they added just diffusion just for fun to the DGCNN model, and they did get sort of much better much better results for that. And then they use sort of this GCN, which sort of helps against over smoothing. And so they applied it to this node classification, which did pretty well, and then did pretty badly on this model 10 net data set. But their data set, so their diffusion data set, did very well on both, right? Which, I don't know, I felt like that was surprisingly good, that it did so good. And so this is the diffusion model, and it still did very well on the model 10 net data set, but okay. And I guess for oversmoothing, they just checked for layers for DGCNN. They didn't actually try to sort of add more layers to this and check how the accuracy changes as you increase your layers, and how bad the oversmoothing actually happens in this DGCNN architecture. But yeah. So these are sort of really good results for this model. And they also sort of train a mixture model where it chooses which chooses either diffusion or a hyperbolic system, depending on the data set. And you can see sort of for the no classification data set, it will it wants the sort of the diffusion equation, and for this sort of shape correspondence data set, it goes for the hyperbolic system.
So a hyperbolic system, the key idea is that it conserves energy. And
Yeah.
for a diffusion system, what is the key assumptions?
As in sort of your feature norms don't increase of time, basically. So again, sort of you can think of it as sort of this flat plate. Sort of if you heat one point and any other point in this flat plate, you're not going to get a hotter region.
Mm.
Right? It diffuses through.
And
Which-
then
Yeah.
is the smoothing a consequence of that assumption that you see like in diffusion case?
Yeah, because again, sort of if you take sort of a point in your plate, and then you take sort of a ball around that point, is going to be sort of the data in that point is going to be sort of an average of the previous.
Okay, and then for Cora, that means that what the representations in the graphs are there's like a good locality assumption where like nodes that are close to each other should have similar representations.
Yeah, basically, yeah.
Okay.
Which at first it was sort of weird to get my head around. It's like, wait, over smoothing, or sort of this diffusion thing is good for this sort of data set. But yeah, so this is what they sort of assume. So they assume like they have this locality assumption, whereas in this model 10 or Faust data set, they have sort of this global.
Mm.
You want to take into account, you do really care about the geometry of your data. And so then they argue that, okay, so this mixture model is really good because it can generalize to, it can be sort of generalizable. So it can work well on this node classification problem and this shape correspondence problem, this like local and global problems, classification problems. Yeah, so they learn PDE dynamics by sort of tuning your alpha parameter there in your mixture model. And yeah, and so they say problems like node classification, you get better performance with the diffusion model and so on. And they do sort of semi-supervised, and they do fully supervised node classification. So in this sort of semi-supervised setting, you can see sort of just how badly the accuracy drops, or just how much it drops as you increase the number of layers. So it goes from like 81% for GCN to sort of 30% at 64 layers, which is massive. And then you get really good results for the PDE GCN, but also for GCN, this GCN II, right, where they try to sort of solve the over-smoothing problem. Actually a bit better results than PDE GCN as you increase the number of layers. And so this is sort of typical with pretty much all three of these data sets as you increase the number of layers. Like you don't really lose that much in accuracy, which is good. So that pretty much solves the over-smoothing problem in this case. But I guess you can also say that, oh, GCN II also does the same problem by just doing a small residual connection in your convolutional graph GCN. But it doesn't have this generalizability. So that's sort of the main benefit of PDE GCN above GCN.
So one thing I'm a bit confused about is, and maybe, yeah, sorry, I feel like I've asked the same question a couple of times, but it's just that I thought that the diffusion equation caused over smoothing as you increase depth.
Yeah.
So they're showing that so the model that they're using is one that causes over smoothing in GNNs. No, like the one that the model of theirs that they're comparing to, the PDE GCN.
So the thing with PDE GCN is you can vary the amount of diffusion that's happening in your model. So usually with this GCN, just the typical GCN, you're just going to get, you will get over smoothing, but you can't sort of control this over smoothing as you increase the number of layers. Whereas with this PDE GCN, you can say that, okay, it's going to learn that the weighting is just going to be much less, so the diffusion isn't going to happen as quickly and so on. But you still want some diffusion happening. Yeah. So it's all about sort of being able to control. Yeah.
So essentially, it adds. Is it? No, there's no hyperparameter. Is there a hyperparameter that controls diffusion, or is it a parameter that's learned?
It's a parameter that's learned. So it would be your. Let's see if I go there. Yeah. So it would be this operator, this G transpose, K transpose, and then KG.
Okay.
Right.
And so essentially, you are, as opposed to GCNs, you allow, this model allows you to learn the rate of diffusion or the rate of smoothing that you want.
Yeah.
Which you wouldn't be able to learn otherwise.
Mm-hmm. Yeah.
Okay, cool.
And if you do a mixture model, I think they say even at one point where they try to test a diffusion model in one layer, and then they test a hyperbolic in another layer, and so on. But that doesn't give as good results as if you do just a mixture model, which I guess makes sense. And yeah, so they have a couple more results here, which is a huge number of results. But yeah, so they do the same test for the protein interaction data set, where actually GCN2 gets better results, but still sort of very good results. And for the purely hyperbolic problem, they get sort of 99.9% for the geodesic error in that. So it works very good. To be fair, the diffusion system still does sort of not horribly on that data set, but yeah. And then they do so they play around with the positive semi-definiteness of your operator. So if they remove this K transpose L, you get here, yeah. So you end up with like a non-symmetric system, and so you do end up getting some oversmoothing happening. So it goes from like 74 to 73 as you increase the number of layers. Not crazy, but you still get some oversmoothing happening there. And so yeah, so that's pretty much all the results, which show that with this PDE GCN network, you can increase the number of layers as you want without oversmoothing happening, and you get pretty nice generalizability to a local versus global classification problem. And yeah, that's it. Yeah. So yeah, so I think it's pretty interesting, and the ideas are pretty interesting, but they should have definitely looked into more different numerical methods for solving these PDEs, and maybe look at some first order or second order PDEs, not just these diffusion and hyperbolic systems.
So the idea behind the hyperbolic version of the model is that it preserves some global quantity of the graph.
Yeah, which I guess in this case is the energy that you have.
And what's the energy of like a graph that's like a citation network or something like that?
I guess it would be, well, you would have to discretize your operators, right? Your gradient and your divergence. And then you could just use the features to calculate the energy of, let's say, in a graph and so on.
Mm-hmm.
That could be a way to do it, yeah.
Okay.
But yeah, so they actually have sort of this Faust data set that they use has like, actually I hadn't seen it before, and they use like human scans of humans doing like different poses. with like a huge number of nodes. So that was sort of pretty interesting to see. I hadn't really seen that before. But yeah, so I think this is useful, and there has been some papers out not too long ago on the same problem where you look at graph neural nets with sort of continuous systems. And usually can do a lot of theory behind it, which sort of gives it a lot of backing and sort of bounds. And so you know that you're approaching some sort of correct solution, or you're actually learning something. And this could actually help with explainability in your graphs, right? So a lot of the time, these algorithms are pretty black box, whereas here sort of you can maybe see, okay, so you're trying to, it's increasing its diffusion, and so on. So yeah, so I hope this was interesting. And yeah, so any questions, shoot.
So I guess the main question I had was, how well does this, I mean, there are some results that suggest pretty well, but how well does this method generalize to non geometric or physical systems, in the sense that these equations are used to model physical systems? And when you start applying it to like arbitrary graph data, maybe like organizations or something like that, like the connection between organizations, does it still apply? It seems like it might. I'm thinking to myself, based off what you said, that maybe the hyperbolic system, in a way, it learns that the quantity to conserve, like what the energy should be or something based on the task. I don't know.
Yeah, because I mean, it did pretty well on sort of data sets that aren't really like have much like natural meaning, like the PubMed data set and the CiteSeer data set and so on. So I feel like it could still, it could still generalize pretty well, I think. I don't see why not. But yeah. Okay, so any
So
more questions?
Yeah, so they have like these two systems. Okay, so they have the diffusion and hyperbolic. And I was wondering if like they have like other type. There could be other type of behavior that you could try to include, and then like try to have something even more general.
Yeah, you can. There are, I guess there are elliptic, but those are sort of, I don't know how much information, or I guess the dynamics would be a bit, I don't see it straight away how, on which sort of data set it would work better on. But yeah, you could have something like you have sort of a first order PDE or a second order PDE, and how sort of the dynamics would change. Maybe you could have some forcing even in your PDE. So yes, so that's why I think sort of this idea of using PDEs with graph neural nets is just a super open idea, and there's lots of things that people haven't tried yet, and there's lots of possible ideas that you can use of different types of PDEs, or different types of discretizations of your PDE, and so on. So yeah, still super open.
Cool. If there are no more questions, If there are no more questions, thanks everyone for attending. And thank you, Nea, for presenting this paper. It is super interesting. And I hope everyone has a good weekend. Thanks all.
See you everyone.